Stat theory. Yes, that's. Yeah. Oh, you're not. So you don't have it. Yeah. You're not in the class. What class are you?
All right, let's start. So we're in section 2.2, linear transformations and their matrices. And the main idea was that if you start with a linear transformation T from a vector space V into another space, vector space W, they're both finite dimensional. Let's say V has dimension n and W has dimension n. And let's say alpha is a standard ordered basis for V, and beta is a standard ordered basis for W. And just to be sure, I'm going to record it in OneNote as well from the beginning. So at least you have some kind of recording afterwards. Okay, so alpha is a standard ordered basis for V, and beta is a standard ordered basis for W. You can associate to T a matrix denoted like this, T from alpha to beta. What size will this matrix be? It's backwards, right? So it goes matrices m by n over the field F, where F is that field that both the V and W are vector spaces over. Okay, so the last thing that we've seen was that if you take two linear transformations, T and U, okay, so those are linear transformations. And let's say A is the matrix of T and B is the matrix of U from alpha to beta. Okay, then we've seen that the sum between T and U will have as a matrix the sum between A and B. And if you take a scalar multiple of T, so let's say C times T, we'll have as a matrix C times the original matrix A. Okay, there are two more ideas in this section that I wanted to talk about. One of them is about the following set. The set L, VW, denotes the set containing all the possible linear transformations defined on V with values in W. V and W, again, two finite dimensional vector spaces over F. So I basically have a set of functions here, right? The functions are linear transformations. And on this set, we're going to consider two operations: addition as above, as in T plus U above, and scalar multiplication, scalar times a linear transformation. So L together with addition of linear transformations and scalar multiplication. Again, scalar multiplication by scalars in F, the common field of V and W. All right, then what's going to happen with this set? If I take two linear transformations, I add them up, the result is still a linear transformation. If I take a linear transformation multiplied by a scalar, the result is still a linear transformation. So this set, L, is closed under the two operations, correct? Where I'm getting with this is that it turns into a vector space. over the same field F. Let's see, there were 8 things in there, right, in the definition of the vector space. So other than closure, which we quickly went through, what else do we need to be a vector? So 0, right? What would be a 0 for this vector space? It's a transformation. It has to be a transformation that would act like a 0. It sends everything, let me call it T sub 0. It sends everything into the 0 of W. 0 of W. So it's the constant 0 linear transformation, T sub 0. Remember that every element needs to have an inverse, right? What would be the inverse of a linear transformation? I'm not talking about invertible functions here, right? I'm talking about inverses with respect to addition. So I'm just taking the negative and putting it in front of the original linear transformation. Then their sum will just be 0, right? And the other properties were related to multiplications by scalars, that they distribute and they're associative and everything. So I'll just wave my hands here and say that everything is fine. It's straightforward. It's going to be. Okay, so this is one thing. And, well, actually, let me give you an example of a question related to this. It is number 13 on page 86 in the book. It says, let T and U be linear transformations such that the range of T and the range of U are not disjoint, but they only intersect in 0, because they are subspaces. Both of them have to contain 0. So they only intersect in the 0 vector. Show that the set containing T and U is a linearly independent set in that space above. Right, so I have a vector space, this L. Its elements, its vectors are in fact linear transformations. And here it is, I have this set containing 2 vectors in that space, so 2 linear transformations. So I want to show that this set is linearly independent. So I would go exactly in the same way about this, right? How do you show that something is linearly independent? You start, as you did on the test, right, with a linear combination equal to 0. So let A times T plus B times U equal to 0, but who's the 0? It's not just a 0, right? It is what we called T sub 0, because it's a 0 of the set of transformations. So the transformation T sub 0. We want to show that A and B must be the 0 scalars. Okay. So we have an equality here between 2 functions, and that means it holds for any element that you plug into those functions. So let me apply it to some element x. That would give us A times T of x plus B times U of x equals T0 of x. T0 was that special transformation that sends everything into the 0 vector of W. Okay, so that's what we have, and there is one additional assumption that we haven't used. What's that? up here. So how are we going to put those things together? All right, so somehow we need to reach some identity involving things in the range of t and the range of u, correct? I have a times t of x, but that's the same as t of ax, right? Because t is linear, so it can incorporate the scalars. And then I have b times u of x, so that's the same as u of bx. But what I want to do is to create some kind of equality between something involving t and something involving u. So I'll move u to the other side and incorporate the negative sign as well. So now we have t of something equals u of something. And we know, of course, this t of something belongs to the range of t, and this u of something belongs to the range of u. But those two sets only intersect in the zero vector, right? Okay. So it must be the case that what you have inside both t and u is the zero vector. Who was x? Well, pretty much anything, right? X was arbitrary, so that's only possible when both a and b are 0, and that's exactly what we wanted, right? In order to show that that set is linearly independent. Okay, so what I'm trying to say is that, you might see examples with vectors being replaced by this kind of linear transformations, but nothing new, right? You just follow the same kind of recipes. All right, so that's one thing. The other thing is something that we'll need later on. Here it is. So let A be an m by n matrix. With entries in a field F. We're going to, so what did we do so far? We had a transformation, we associated to that a matrix, right? That's what happened in this section 2.2. What I'm going to do now is to go backwards. I have a matrix and I'm going to associate to it a linear transformation in the following way. It's customary to call it L sub A. So L sub A will go from, I want this transformation to have A as the associated matrix, okay? And it's m by n, so it has to go from a space of dimension n into one of dimension m, to get to m by n. So Fn to Fm. And this is just the left multiplication by A, hence the notation L sub A. So L sub A of an x, where x is an n tuple, right, in Fn. So you can imagine it as an n by 1 vector if you want, right? Is A times x. So again, if you think about matrix vector multiplication, you can see x as an n by 1. A was an m by n. And x is an n by 1. So the result of A times x is what? M by 1, right? So I end up with a vector in Fm. Right, so started with a vector in Fn, ended up with one in Fm. So is it clear what this does? So basically you have a matrix and you multiply that matrix to the left, right? With, so for example, let's say A is 1, 0, 2, 1, 0, 3. It's in matrices 3 by 2 over F over R, in fact. Who is L sub A? So L sub A goes from R2 to R3. L sub A of X is A times X, right? By definition, left multiplication by A. So basically, if you take a vector in R2, which looks like this, x1, x2, you need to put A, which is 1, 0, 2, 1, 0, 3, times x1, x2. Right, so it's a 3 by 2 times a 2 by 1. It results in a 3 by 1 vector, which is x1, 2x1 plus x2, and 3x2. Vector in R3. All right, so this is how it acts. So let's go back to the definition above. Basically, I started with a matrix and defined a function. I don't know yet that this function is a linear transformation, although I would like it to be, so let's check that. Not the one in the example, I mean in general. L sub A is a linear transformation. So in order to check that, all I need to do is to apply it to a sum like this. L sub A of Cx plus y. L sub A is left multiplication by A. So this is A times Cx plus y. But, you know, we have those properties of matrix vector multiplications. I can distribute the A, I can pull out the scalar. So I can rewrite this as C times AX plus A times Y. Okay, but then this is C times AX is left multiplication by A applied to X, and AY is left multiplication by A applied to Y. All right, so this proves that L sub A, as defined, is indeed a linear transformation. Okay, so now I don't want to just define a linear transformation. I want to define it in such a way that the matrix of L sub A is that A. So the connection between them is, you know, deeper than just, you know, multiplication or something. So let's just look into that. So let's just say that beta is the standard ordered basis of Fn. If you think about Rn, that would be E1, E2 up to En in that order. And gamma be the standard ordered basis of Fm. Okay, so beta and gamma are the standard ordered basis of Fn and Fm respectively. All right, so I want to compute now, I want to find the matrix of this linear transformation L sub A from beta to gamma. So remember that beta is going to be E1 through En. I'm kind of hesitant to write it like this because it seems like there is an overlap between the two bases and they have nothing in common, right? Because in beta, we have vectors n by 1 or n tuples. Gamma contains m tuples, right? But the notation in the standard sense is the same. So E1 here means 1, 0, 0, 0, but how many terms? All together n terms, right? And this E1 means 1, 0, 0, 0, 0, but all together m terms. So I don't know if you want to maybe call them prime or something, so it's not the same thing. Okay, so to find the matrix of a linear transformation, you have to apply the linear transformation to the elements of some basis of the domain. So I'm going to compute L sub A of E sub J. So the transformation is left multiplication by A. So this is just A times E sub J. So it is my M by N matrix A times an N by 1 vector, which looks like this. In position J, right? So this is N by 1, this is M by N. In position J, I have a 1 and I have 0 everywhere else. So my question to you is, what happens when you multiply a matrix by this kind of vector? What do you get? How do you multiply a matrix by a vector? You just take row 1 times the vector, right? That will give you the first entry. So what will that be? If I do row 1 of A times 0, 0, 0, 1, 0, all I will keep from that is A1J. Everything else will be multiplied by 0. Row 2 of A, right? To find the next entry, I do row 2 of A times that vector. What do I get? A2J. How many rows does A have? M. So the last entry will be AMJ. Okay. But remember the basis of Fm, E1 prime, E2 prime, and so on? This is, in fact, A1J, E1, let's call it with prime because it's m-dimensional, plus A2J, E2 prime, plus AMJ, EM prime. So basically, it is the sum I equals 1 to M, A, I, J times the elements of the basis, EI prime. All right, but now if we try to remember how we define the matrix of a linear transformation, we define it exactly like this. We took the transformation, applied it to the jth element of the basis, and we needed this kind of sum, with this being the ij entry of the matrix that we're looking for. So the ij entry of L sub A, from beta to gamma, ij entry, is aij. Who is aij? The ij entry of A. So since they agree entry-wise, the matrix of L sub A is in fact A. Okay, so we took a matrix, we associated to that a linear transformation, whose matrix turns out to be the original one, right? So the association is going back and forth, let's say. Okay. One more idea about this association. So let's say furthermore. let's say A is M by N. B is N by P. So A times B makes sense, is going to be an M by P matrix, right? So I'm going to look at left multiplication by the matrix A times B. This transformation, when applied to a vector, so first of all, where was the domain and codomain of L, A, B? Yeah, like what are the spaces? So Fn? To where? You're thinking it goes from Fn to Fm. That would be L sub A. Fp to Fm. Because A times B is an M by P matrix. So it goes, right, it's backwards. So it goes from Fp into Fm. Correct? When you multiply A by B, you're going to get an M by P matrix. This is A times B. What does this do? This is left multiplication by the matrix A times B. Okay, but matrix vector products have this nice property that they are associative, so this is the same as A times Bx. Okay, but A times something is in fact left multiplication by A, correct? So I can rewrite this as L sub A of Bx, of the vector Bx. Because I'm doing left multiplication by A applied to the vector Bx. And I can keep going because the vector Bx is in fact a left multiplication by B. So this is L sub B of x. So what we've shown here is that L sub AB is in fact the composite function, right? Is the composition between L sub A and L sub B. And this is, in fact, the direction in which we're going in the next section with the composition of linear transformations. So what happened here with these special transformations, left multiplication, was that we took the composite of two of them. The matrix of one was A, the matrix of the other one was B, and we got a linear transformation still whose matrix is A times B, correct? So that's something that we're going to show in general. So if you give me two arbitrary linear transformations, not this type, L sub A or anything, right? T and U, and we can compose them so their, spaces are nice to be, so we can compose them. Then the composite function will still be a linear transformation, and its matrix will be the product between the matrices of T and U. Okay, so this is what we'll do next. Section 2.3. Composition of linear transformations. And matrix multiplication. Okay, so before we keep going with formally proving what I just mentioned, I just want to remind you one thing. So if we have two matrices, so let's say A is M by N, and B is N by P. Then A times B, right, is M by P. And there is a nice way in which you can compute the ij entry of the product between two matrices. There is a formula which says that it is the sum of aik, bk, j, k going from 1 to n. You remember this formula from undergrad? No? So that's just, you know, how to compute the product entry-wise. Okay. I know. I'm going to take a linear transformation T from V to W. Okay. Let's say V has dimension n, W has dimension m. Alpha is a standard ordered basis for V, beta is a standard ordered basis for W. So it has a matrix associated to it, P from alpha to beta, right? Which is an M by N matrix. All right, let's take a second one. U goes from W to a third vector space. Let's call that Z. W had dimension M. Z, let's say, has dimension P. Beta was the standard or the basis of W, and let's say gamma is the one in Z. So it has a matrix associated to it, which is the matrix of U from beta to gamma. Okay, so now I can form, you know, just by function composition. I'm going with T from V to W with U from W to Z, so I can form the composite function. U composed with T, which goes from V to Z, right? So I do V to W with T and W to Z with U, so I can do U composed with T from V to Z. Okay, so this is a map so far. I don't know anything about it, right? But I have two questions. So question one, is this composite function a linear transformation still? And question two, if yes, what would be the matrix of this composite function? So it goes from V, which had the basis alpha, to Z, which had the basis gamma. So I want to know what the matrix from alpha to gamma of this composite function is. Okay. So from that example with left multiplication transformation, we expect the composite function to still be a linear transformation. And what do we expect the matrix to be? Exactly the product between two matrices above. All right, so let's look at question one. So U composed with T, I want to see if it's linear from V to Z, so I'm going to apply it to Cx plus Y. Okay, it is the composite function, so it is U of T of Cx plus Y. But T was linear, right? So T of Cx plus Y is C T of X plus T of Y. All right, but U is also linear, so I can distribute U now, and this is C times U of T of X plus U of T of Y. Which is just C times U composed with T of X plus U composed with T of Y. So we're done. It is linear. Question 2. And I don't know if you realize that again, it's getting more and more hard to see what is written. I think the battery is dying now, but that's another story. Hopefully it will last until the lecture today. Okay, question 2. What was the matrix of the composite function U composed with T from alpha to gamma? So in order to find that, what do I need to do? I need to apply U composed with T to the J vector in alpha. Now, alpha was a basis, so let me give some names now to the vectors in alpha, beta, and gamma. So let alpha was a basis for V, which had dimension n, so let me call the vectors V1, V2, Vn. Beta was a basis for W, which had dimension m. W1, W2, Wm. And gamma was a basis for Z, which had dimension p, so let's call them Z1, Z2, Z, P. Okay, so I'm going to take the composite function ut and apply it to the j. It goes from alpha to gamma, right? So I'm going to apply it to Vj and see what happens. So this is U of T of Vj. Okay. Now, T had a matrix from alpha to beta. Let me call it A. And U had a matrix from beta to gamma. Let me call that B. Because T of Vj has a certain expression in terms of the entries of the matrix A is going to be the sum A, I, J times the basis of W, which is beta. So the sum of Aij, Wi. Okay. But this is U of a linear combination. U is linear, so it distributes. So this is the sum. I equals 1 to m Aij times U of Wi. Okay, now U was a linear transformation whose matrix we called B, correct? So let's keep on going. So if the matrix of U is B, U of Wi is the sum of B K I Z K, where K goes from 1 to P. So now finally, sum I equals 1 to M of sum K equals 1 to P of, let me write this backwards, BKI AIJ ZK. The reason I want to write it backwards is because at this point you should recognize that formula that you're saying you don't remember. The formula for the IJ entry of a product of two matrices, which was written here. All right, so the sum is over this index that is in the middle, AIK, BKJ, so I'll go back here. I want to sum over I, so I'll switch the two sums. And now this sum represents the KJ entry of this product. Basically, what we got is this. The composite function applied to Bj is the sum K equals 1 to P of the product between those two matrices, entry Kj times Zk, which is exactly the formula that defined back then the entries of the matrix associated to U composed with T. B was the matrix of U, T is the matrix, A was the matrix of T, so it's the product exactly in that order. Okay. So basically, if I want to write this nicer, it's going to look like this. Okay. So other than the computational examples in this section, where you're asked to compute, you're given linear transformations, you're asked to find the matrices of each, and you're asked to show, based on that example, that the composite function has the product, and so on and so forth. Here is an example that is less computational. 11 on page 97. Says, let T going from V to V be a linear transformation that it is related to composite functions, not necessarily to matrices, but T squared equals T0 by T squared, they mean T composed with T. Okay, I'm not going to multiply them or anything, I'm just going to compose them. So T squared is T0 if and only if the range of T is a subset of the null space of T. Let's look into this. I think I want to go in this direction first, backwards. So I'm going to assume that the range of T is a subset of the null space of T. And I want to show that T composed with T is T0. Okay, so which basically means that T squared of x is T0 of x for every x. So I'm going to need to look at T squared of x, which is T of x. And that needs to be the same as t0 of x, which is 0, right? So based on the assumption that the range is part of the null space, you see why t of x should be 0. Yeah, because this thing here, the inside one, is of course part of the range, which is part of the null space by assumption. So then when you apply t to it, right, when you apply t to something in the null space, you get a 0 vector, right? That's what defines the null space. So you're going to get 0. Okay, backwards. So I'm going to start by assuming that t composed with t is t0. And now I want to show that the range is a subset of the null space. So basically, I have to show an inclusion of sets, which is done by starting with an element of the set on the left and showing that it belongs to the set on the right. So let's say y be an element of R of t. I need to show that y is in the null space of t. So I know that y is in there, and I know this, right? That's pretty much all I know. So if y is in the range, what can I say? What does it mean to be in the range? It is t of some x. So y is t of x for some x in the domain of t, which is what? V. For some x in V. So looking at what I want to show, which is that y is in the null space, that means I have to show that t of y is 0, pretty much, right? So I need to look at this t of y. T of y is t of x, which is t squared of x, right? And t squared, we know, is t0. So t of y is 0, and we are done. Okay. Move on. So with functions, back in calculus, let's say, when you compose, right, we composed functions in the previous section, but in calculus, the next step was to talk about invertibility, right? Because there are functions for which there exists another function such that the composition is the identity function, correct? Linear transformations are functions in particular, so it's a natural question to ask here, what happens, are there invertible linear transformations, and what properties do they have? Okay. Invertibility. And isomorphisms. So we start with a linear transformation from V to W. And let's just assume that as a function, it is invertible. What would that mean? A function Well, it has to go backwards, right? That function, the inverse, the supposed inverse, would go from W to V. It's called the inverse of t. If the composition between the two in both directions, right, should give you the identity. So if I do, let's say, t composed with u in this sense, then I'm going from W to W. So this should be the identity from W. And if I'm going backwards, start with t first and then apply u, I'm going from v to v, so I need to have the identity function on v. Right, so that's the function that takes x into x for every x in v. And from the theory of functions, if a function is invertible, its inverse is unique, right? And it's called t to the power -1, if it exists. Okay, but no word about the fact that t was linear, right? So if we have this additional assumption that t is linear, does this function u, the inverse, have, additional properties? And the first question, natural question here is, will the inverse still be a linear transformation? And the answer is yes. Theorem. Let t be a linear transformation from v to w that is invertible as a function. Then its inverse, to -1, going from w to v, is also a linear transformation. So basically, I have to show that a certain map is a linear transformation, and I'll just go with the definition. Actually, I need to show that the inverse of Cx plus y is C T inverse of x plus the inverse of y. And that should hold for any x and y in W. All right, so I want to get back to t now, and here's how I'm going to do that. X and y are here, right, in W. T was invertible as a function, right? Remember from calculus that invertible is equivalent to being one-to-one and onto, correct? So this function t, the linear transformation, has to be both one-to-one and onto. Now, because x and y are in W and t is onto, they are the images of some vectors from V through t. So since t is onto, t of some, I don't know what to call them, v1 is x, and t of v2 is y, for some v1, v2 vectors in V. Okay, so let me put that back into the, the left side of the identity we need to show. We're looking at T inverse of Cx plus y. And x we said is T of V1 and y is T of V2. Okay, but t was linear, so this expression here can be, you can move everything inside t, and it's going to look like t of c v1 plus v2. Okay, but this is just t inverse composed with t applied to cv1 plus v2. And v inverse is supposed to be that map that is the inverse, t inverse is the map that is the inverse of t. Therefore, the composition is just the identity function, right? Identity applied to cv1 plus v2 will be cv1 plus v2. Okay, let's keep on going because that's not what we need. We need this. But v1 is defined here, and it is the same as t inverse of x. And v2 is defined here, and it is the same as t inverse of 1. So we're done. It is indeed linear. Remember one thing, so invertible is equivalent to being one-to-one and onto, but we've seen something before for linear transformation that said in case the v and w have the same finite dimension, one-to-one and onto are equivalent. We've seen that, we proved that before. So keep that in mind, that invertibility in case v and w have the same finite dimension is equivalent to one-to-one or onto one of them. So note, if v and w have the same finite dimension, then t is invertible if and only if t is, let's say, onto, if and only if t is one-to-one, because we showed that onto and one-to-one were equivalent in this setting.
We have one of those three.
You have everything, yes, but again, under that assumption. Equal and finite. Okay, but now you have a linear transformation that maybe has an inverse, right? Which again is a linear transformation we've seen. A linear transformation has associated to it a matrix, right? The composition we've seen has associated the product between the two matrices. So what should be the matrix associated to the inverse of t then? For everything to make sense in this picture. Let me be more precise. So I go from V to W. T has a matrix, alpha and beta, right? Let's call that A. And T is linear. Let's just assume that T is invertible, right, as a map. There exists T inverse going from W to V. The inverse of T, which is also linear, because we just proved that. The inverse going from W to V, so from beta to alpha, will have a matrix associated to it, B, right? Okay, but being the inverse, what will this composition be, let's say? So I go first with T inverse and then with T, so I go from W to W, right? This is the identity on W. On W, the basis is beta. So going from beta to beta. Now, this 1W is the identity transformation, right? It takes every X into itself. What's the matrix of the identity transformation in a basis, any kind of basis? So I have a basis beta, W1 through Wn. And this transformation, 1 identity, right? To find the matrix of the identity, I need to apply it to, let's say, the jth element of the basis. What do I get? Identity doesn't change anything. So I get Wj. But formally, I get this. So what does this tell you? What are the Aij? Well, this tells me that Ajj is 1. Do you agree? Because only Wj appears on the left. And on the right, I have all of them. And everything else is 0. They don't show up. It's just Wj there. So what kind of matrix is this? This is the identity matrix, right? It's the most natural possible answer is the identity transformation. Its matrix, the associated matrix will be the identity matrix. Identity M by M, M being the size of the space, the dimension of the space. Okay, let's move towards the left here. We've seen that a composite function has as the associated matrix the product of the two matrices, right? So this is the matrix of T from alpha to beta times the matrix of T inverse from beta to alpha. What did we call them? We call them A and B, right? So A times B after all is the identity M by M. I can also go backwards if I want, because T inverse composed with T backwards is still the identity. So B times A will also be the identity. Maybe B times A is the identity. So what does that tell you about matrices A and B? Yeah, they are inverse to each other, right? So B is the inverse of A. Let me rewrite that with the terminology above. So the matrix of T inverse from beta to alpha is the inverse of the matrix of T from alpha to beta. So basically, you're allowed to pull that -1 out. Now, a little bit about the dimensions here. In this kind of argument here, I said the dimension of W was M. What about the dimension of V? Can I call that N? I mean, what's going on here? Because if the dimension of V is N, what size would A have? A would be M by N, right? Can an M by N matrix be invertible? No way. So I can only talk about square matrices here, okay? Why is that? Well, it all comes from this assumption here, that T is invertible, right? Once I'm making the assumption that an inverse exists, it has to be the case that, you know, if they are finite dimensional, that the dimensions are the same. Right? So let's show this in general. Let's say note. Let T be a linear transformation that is invertible. Then V is, so it's a bit more than I said, but V is finite dimensional if and only if W is finite dimensional. In this case, they must have the same dimension. So what is this saying, in fact? There is no way I can have an invertible transformation between a finite dimensional space and an infinite dimensional space. Okay, that's the first idea. So they must be both finite dimensional. If they are both finite dimensional and I have an invertible transformation, it's exactly as we noticed above, the dimensions must be the same. Okay? Let me try to prove it if this pen will allow. It's kind of dying, I see. So let's see that if and only if thing first. So if V is finite dimensional, let's just say it has a basis of n elements. Then I'm going to look at the range of T. The range of T is the span of T of V1 through T of Vn. But I just assumed that T is invertible, right? Being invertible means it is in particular onto. So the range is everything, right? The entire codomain, so the range is W. Okay, so here is a finite set then that spans W. It's a generating set, so it can be reduced to a basis. So W has a finite basis. And we're done, right? Because I wanted to show that W is finite dimensional. If I want to go backwards, I'm not going to rewrite everything, but if I want to go backwards, I'll go with T inverse and exactly the same idea. I'm going to use the linear transformation T inverse from W to V and say that W has a finite basis, W1 through Wm, let's say. Move everything over with T inverse and get the range as a span, and V will have a finite basis. So that's the first part. So if the dimensions are finite, then dimension of V has to equal dimension of W. So let's see that. Let's show this in general. Okay, so all we know is that they are finite dimensional and that we have a linear invertible transformation between them. I will just make use of the dimension theorem. What does that say? Dimension of V equals the rank plus the nullity. So dimension of the range plus the dimension of the null space. Okay, but T is special. T is invertible, right? So T is 1-to-1 and T is onto. So what does that mean? The range is what? The range is W, right? Because T is onto. Because T is 1-to-1, what is the null space? 0. The 0 vector only. Okay, so let me rewrite this. Dimension of V equals dimension of W plus 0, right? Dimension of the vector space containing 0 is 0. And by the way, its basis is the empty set, not the 0 vector, right? I've seen that in the test a couple of times. That's why I wanted to point out. Okay. So we're done, right? They must have the same dimension in the end. All right, so let's just stop here. We'll continue next time.